各位线上的朋友，大家好，我是百度的王冲，欢迎各位参加百度 Apollo Day 在经历大浪淘沙，可以看到两极分化的趋势。是否可以做到全无人落地，就是这场考验中的试金石，决定谁可以率先脱颖而出。今年8月，百度已经跨越了这道分水岭，首批获准在武汉、重庆全无人商业化运营。最近又在北京开启了全无人内测，这一切的底气来源于长期不懈的研发投入、扎实的技术积累。今天我们有幸邀请到了自动驾驶技术领域的6位专家，分享他们的实践和思考，与大家一起探寻百度无人驾驶的技术之路。首先有請陳靖凱。
大家好，我是百度自动驾驶的陈靖凱。众所周知，百度在自动驾驶领域已深耕多年。今天我们给大家分享我们在打造安全、智能、高效的自动驾驶体系中的一些思考。自动驾驶系统最重要的是安全，系统设计需要遵从汽车安全体系。我们从功能安全和一级功能安全2个方面来打造我们的自动安全系统。按照功能安全的设计要求，我们拆解了系统的安全框架和目标，通过适当的冗余来降低失效带来的危害。我们在计算硬件、传感器、底盘、通讯的各个层面都构建了冗余，并且完善了故障检测和处理方案，实现全方位的安全。传统的安全设计主要是保障司机的可操作，使得司机在故障发生的条件下有能力处理相应的故障。在自动驾驶系统中，我们需要能够让自动驾驶系统处理这些故障，保证系统安全。自动驾驶系统不仅仅要处理自动驾驶系统本身的故障，而且要对车辆的各个系统的问题也做出相应的应对。比如说，当车辆的胎压系统出现问题的时候，我们需要让它能够检出来，能够在车辆运动可能会出现异常的情况下，把车辆安全停下来。但商业运行会让系统变得不够安全。我们的安全策略是让车辆在发生故障时只是进入安全状态，而不是技术保持驾驶。这时候呢，就给我们提了一个不同于主系统的挑战，就是如何在各种各样的道路条件下，当我们发生故障的时候，把车辆进入安全状态。在复杂的道路条件下，我们是不能以简单的一个标准。故障方案必须与真实的道路条件相兼容。我们充分的利用了绑定系统，去测试一下我们的故障处理策略是不是能够应对当前的故障，能够应对当前的道路条件。进入安全状态。通常和完全的系统
And our safety strategy is to bring the vehicle into a safe condition when a failure occurs, rather than continue to keep it driving. And the time presents with us a different challenge than the primary system, which is to how to bring the vehicle into a safe state when we have breakdown in a wide variety of road conditions. And in complex road conditions, we cannot simply stop and then just let it stop there. The failure scenario must be compatible with the real road environment. We make full use of the simulation system to test whether our fault handling strategy is able to cope with the current problem. And the capabilities required to enter a safe state are usually not the same as those required to complete a fully functional autonomous driving system. Often, actually, the need is quite small, and here we have a challenge, and also we have the opportunity to balance the reliability requirements with the cost. And then a reasonable safe driving strategy is especially critical at this point, and we have conducted a lot of testing in the simulation system to adjust our safe handling mechanisms so that we could strike a good balance between the two. And the evolution of the capabilities of the autonomous driving system is actually developed in accordance with the expected functional safety. We will advance the capability of the autonomous driving technology from the 2 dimensions of knowing or not knowing and safety or non-safety to improve the adaptation of the autonomous driving system to the complex scenarios. As we know that a reasonable defined ODD is the to grow part of the autonomous driving system, especially a fully autonomous driving system, we need a lot of simulations and road tests to guarantee our safe driving within the ODD. However, autonomous driving is not perfect and road conditions are complex. It is usually not very realistic for us to think of a detailed definition of ODD, especially one that includes the dynamic interactions, and so we usually still favor static definitions in the general ODD definition, and makes it difficult to cover all road interactions scenarios. At this point, we need to have a strong detection capability on the vehicle to detect whether our current system is running under ODD, and even then we will encounter some states that are beyond our autonomous driving capabilities. And this time we designed a system that uses our practical data to design our just a warning strategy for our current driving capability, which allows us to better determine whether our current system is in a potentially unsafe state, and then we will supplement it with some cloud road test and to ensure safety so that our system can change from potentially unsafe state to a safer one. The system will change from potentially unsafe state to a more secure state, and this kind of work will definitely have a certainly compromise on the efficiency of the autonomous driving. As our autonomous driving capability improve, and we will know fewer and fewer unsafe states and scenarios, and the corresponding autonomous driving efficiency will gradually improve. And on the vehicle side, and we will allow this idea to make the corresponding treatments. We will build some safety loops outside of the main system to ensure the safety of the autonomous driving system in some scenarios and under some unexpected conditions. The capabilities of the autonomous driving system is still in the process of a continuous improvement. And we need to turn more problems that we don't know into problems that we know, and turn scenarios that could not be just handled safely into scenarios that could be handled safely, and we can anticipate some possible dangers and avoid some complex and dangerous scenarios through strategies. And we need to have a data mining system on the vehicle to help us discover these problems. Through data mining on the vehicle side, we will continue to find out what is not handled well enough in the autonomous driving system or some uncertainty issues, and then upload those data to the cloud through the cloud system. We use data-driven way through training, simulation, and serious work to improve our autonomous driving capabilities and to improve the safety of our autonomous driving. And then let me briefly introduce Baidu's autonomous driving technology system to you, and then how should the autonomous driving system be designed. There have two methods, and one is the academic one, tend to be the unified modeling and end-to-end problem solving, and the other is based on the engineering and to split the system and then have breakthroughs one by one. And then for the end-to-end modeling, it is quite simple and just neat, and then in the long term, it is quite promising. And then under such thinking, actually, we have some progress in other areas. And then, for example, the technology models have achieved dominance inside the NLP domain, and then in the image, the big model has give us many progress and similar, and we are excited about the end-to-end big model solution for the autonomous driving system. And the problem here is that we still have lots of uncertainty. We are not sure exactly when it will mature and whether it takes 2 years or 10 years to complete and make through. And based on such perception, and now we're going to move forward along the engineering route. And while we haven't given up on our end-to-end just a pathway, and in exploration, we're going to apply some of our milestones to some of our routes. And then for the onboard system, it has four parts: the map, perception, prediction, design, and planning and control. And the map is very important in the system, and then we discuss about it a lot. The autonomous driving system cannot be separated from the map in development because the traffic system is originally a system under the constraints of the rules. Autonomous driving is running under the actual conditions of traffic. Of course, it cannot be separated from the constraints of the rules, and the maps are precisely the core framework. And we believe that regardless of whether there is an offline map or whether I can just use an online map, the map is always an underlying expression of the autonomous driving system. And the offline map is quite important, and it is over the horizon holistic perception, and we believe that it plays an important role in the autonomous driving system. When we talk about the offline maps, we usually are just thinking that whether it is quite expensive to just make the offline maps, and then will it be an obstacle for us in the development and in our practice? We found that the offline maps are actually not expensive. Actually, it is a driver for us to move forward, and the update rate of the map is not a problem. And then the problem lies that when we first encounter the real world changes, and we certainly do not have the map updated. So at this time, we need to able to just make sure that we have the real-time updated map, and then the update rate and its cost are not that important. Let me talk a little bit on this issue. We all know that it is not difficult to just solve a problem. The problem lies in that whether we could solve all the problems one area, and this is quite challenging. And in our practice, currently we have a gap in quality between the real-time production of the maps and the large-scale production of the maps on the vehicle side, and we need to adapt to the quality differences. And between these two types of map through our autonomous driving strategy, but this adaptation isn't a compromise to the ability of the autonomous driving. And we believe under the current situation, scale production of the high precise maps is quite important, and real-time maps will be used more by us to cope with real-time changes. And when we will adjust our autonomous driving to a safer and more cautious way. And later, Jizhuo will share more details in this area. For the perception system, it is relatively unified in the industry about its development, and mainly it is a data plus the model-driven system. At present, our main disagreement is about some of the main differences in the configuration of the sensors. And in our opinion, we should go to fully explore the capability of each sensor, because our starting point is to have a better and lower cost development, and this is our thinking. And here we would like to fully explore the capabilities of each sensor to make the perception more reliable and more stable. And in the specific process, we move from just a late fusion solution to our early fusion solution, and that allows us to fully explore the advantages of each sensor. In addition, we will fully use the accumulation of Baidu's large model technology to enhance our perception capabilities, and later Dindo will share more details. For the prediction decision system, and it is quite an important part of our strategies to deal with the external environment. And we put the system, and usually we could see that we put the system of we put the system module of the driving line between the prediction decision and the plan control, and the main for us to start, and then the decision problem actually could be just supported by the artificial judgment, and also we're going to contribute to more human intelligence. Here we could put the prediction and decision making together, and then also we have some thinking in this scenario. And in fact, in the real world, we have the interaction between the vehicles and the real world. So we more inclined that the prediction and decision making are intertwined, and lots of the prediction is based on the decision making. And for the planning and control, that the planning and control is an optimized problem, and then in the traditional method, and we often face some conflicts between the solution space and the computational resources under the real world conditions. And in this scenario, we have also done a lot of exploration, and here we're going to share with you some of our work. As we mentioned together, the driving capabilities is shown on the vehicles, and more work is should be done in the cloud and in the iteration of the onboard system. And we should learn from the data, learn from the issues, and especially for the autonomous learning, this is what we are aiming for. So we establish our closed loop data system, and currently we are having iteration and in the technologies and trying to improve our technology. And the system later Liang will share with you more. And for the simulation system, and it is always quite an important topic for us. And then our perfect simulation system and is what our developers are aiming for, especially when doing some end-to-end exploration. And we will feel that quite happy if it would be to have a perfect simulation system. And then it is impractical to make a perfect simulation system at the moment, because if we want to simulate various driving scenarios and styles in the simulation system, then this driving scenario and system is exactly the same as the humans, and we actually make our autonomous driving system with different personalities, and this is quite difficult and impractical at this stage. And then the goal we are pursuing to make the simulation system useful for improving our autonomous driving technology capabilities, and we will introduce to you some of the work later, either for the onboard or the cloud system. Autonomous driving and needs the support of a computing power, and we will have more works in this area. And then later Ouyang will introduce about the equivalency and then its application in the autonomous driving system. And thanks to the development of the autonomous driving technology and autonomous driving system we built, we will developing a fully autonomous driving system to provide better travel services for everyone. And later we will develop the advanced assisted driving to provide drivers with a better driving experience. Later on I will share with you about this one. And for our initial autonomous driving system, the prediction and the decision making are separated, and the prediction is our task, and with self-labeling, and have always been data-driven, and while decision making and planning and control are all traditional rules-based solutions. And for the rules-based solution, we usually divide the encounter problems into various scenarios, and in each scenario, and we could see the different problems that arise, and then we will deal with them correspondingly in order to prevent conflicts between the various rules. And usually we will carefully limit the scope of each rule, layer by layer, then split them down. If done well, we will perform our quite tree-like split structure, and if not handled well, it becomes a system of patches. And because we're going to add patches on top of the patches, especially in the later condition, we can not just deal the problems well. And even if the former we are highly sophisticated good tree structure, we will encounter some problems that our cognitive upgrading leads to a current tree structure, and our cognitive mismatch. And then in the very beginning, the rule system is able to maximize human experience and some of the previous knowledge, and can quickly go to improve the autonomous driving system, but as time goes by, two problems will eventually arise. And the first is the police purification, and which leads to what? Resulting each iteration of the rule, and for the problem, they will become smaller and smaller. And then second, we need to adjust to the rules, and then to adapt in the face of the urban expansion. And then later, the scope of this adjustment is often not limited to the notes on the leaf, but still we need to have the comprehensive adjustment later. We're going to have, if we do not do that later, it's going to quite hard to do the maintenance. And because of that, we think that the PNC is quite important. As we mentioned before, prediction and decision making are two sides of the same problem, and the prediction is the self-realization of our decision. So we construct a multitasking system for prediction and decision making to jointly deal with this problem. And we have some modeling and interactive processing on road elements, on signals, on self-testing behaviors, and on road elements. We finally form our prediction and decision making. One result, the idea of this work is still quite basic, and in our practice there are many interesting problems. So for each learning system, we face the startup and the iteration problem, and also we will think that about the relations between the old one and the new one. Also, we adopt the gradual progressive idea. And for example, the rule system actually the learning system, and we have to initialize our learning system about the conditions of our experience and the rule system, and then through some iteration, our learning system will surpass the rules. And so now let's talk about the simulation system. As we mentioned before, we have to make a quite useful simulation system. And so we know that it is quite hard to build a complex system that could deal with other scenarios in the simulation. And also in the process, we know that simulation is quite important. And currently, we have a team of several hundred staff, and they are to mimic the development of the autonomous driving, and also to develop the possibilities in the simulation system. And as we know, even for only one case, if we would like to achieve the practical simulation, it is quite hard. And then we currently have to overcome the difficulties in our simulation. And currently, we have different strategies. And later, it is going to have the interaction between the vehicles and the environment. So here, we have to know that how to deal with the problems. And for example, currently we have some problems like the overtaking of the vehicles. And then, so in such a scenario, and how could we make sure that the situation is better or not? So in the practice, we will find that we could not discuss this problem if we are separated from the large-scale data distribution. So in the simulation system, we have to build the good data collection, and the data is the key of the simulation system. And also, we're going to have different scenarios on the road, so we have to establish the rich database. Based on the scenarios, then we will compare the database with the roads. Then we'll see the coverage rate of the data about the real scenarios. And also, we could see that most of the scenarios could be covered by the data, and about 600 to 700 scenarios. And then later, in the generalization, we see that many of these scenarios don't need to be generalized. And so at that time, and we're going to have a more detailed dimensional breakdown of the common 700 scenarios. And this is because for example, for the overtaking, and we will collect data about the models of the car, and then the speed, distance, and then also the time for the overtaking. And then we're going to build up the dimensional system based on this scenario. So we're going to establish the data set based on this scenario. And then we will see the simulation is realistic or not based on the real scenarios. And so we're going to, based on that, construct a correct metric for the condition of a relatively distorted distribution of the simulation system. And this metric is not a scenario generalized from the world season, and as we mentioned earlier, why? And because actually in that scenario, and we have lots of the parameters like the behavior of the vehicles, and we have to connect the simulation with the real world so that to make the vehicle operation more realistic and reliable. And also we have built a system, and we have built some specific scenario database and for our specific needs, such as the traffic regulations, and then also for the safety. And then we built a library of scenarios so as to fully read them, and also to make an assessment about each of the update. And also we couldn't know that from the mobility from one city to the other, and we have the changes in the distribution of the data statistics and the distribution, and so we have to make some adjustment. And all in all, the simulation system is quite important. And now we'd like to welcome Huang Jizhou to share with us about the rethinking maps for the autonomous driving Apollo's practice and insights. Now let's welcome.
Good morning, I'm Huang Jizhou. Today I'm going to talk about rethinking maps for autonomous driving, Apollo's practice and insights. If you look at the maps used in cars carefully, you'll figure out that the car intelligence is the core driver for map changes. And the earliest maps used in vehicles are standard definition maps, or SD maps. They're used for navigate. And SD maps are mainly composed of coarse-grained road topology information with low accuracy, usually around 15 meters. With the development of automatic intelligence, especially the development of assisted driving and autonomous driving, the requirements for map accuracy and richness of elements are becoming higher. And lane definition maps, or LD maps, are mainly used for assisted driving. LD maps incorporate lane-level topology information and are generally sub-meter in accuracy. High-precision maps, or HD maps, are mainly used for autonomous driving. Compared with LD maps, HD maps have centimeter-level accuracy of elements and also contain rich semantic information. In order to make autonomous driving safer, more comfortable, and more efficient, in addition to rich and more accurate topological, geometric, and semantic information, we need to rethink and redefine the maps needed for autonomous driving from the perspective of the industrial needs of autonomous driving. With regard to the relationship between the high-precision maps and autonomous driving, some L2 intelligent driving recently mentioned the idea of a focus on perception rather than maps. The main reason for putting forward the idea is that it is difficult to overcome the three major obstacles faced by HD maps, namely qualification barrier, self-research barrier, and supply scarcity. By a qualification barrier, I mean it is really difficult to get the qualification of surveying and mapping. And by self-research barrier, I mean the high cost of R&D caused by the high technology barrier and the long research and development time. By supply scarcity, I mean we are the only company in China that is both proficient in maps and deep in autonomous driving. Regarding the relationship between HD maps and autonomous driving, our view is that maps that care about user experience with lower cost are essential for autonomous driving. First of all, to achieve safety and sustainable L2+ smart driving products, the role of high-precision maps is crucial, and there's no substitute. And as for this point, and Mr. Wang Liang will deliberate on that. And my presentation is mainly about the L4 autonomous driving. And for L4 autonomous driving, if you want to reach over 99.99% success rate, HD maps are critical and indispensable. First, about cost reduction. We have improved the intelligent production capacity of high-precision maps so that we can achieve continuous cost reduction with the same accuracy and quality. Second, about user experience, we mainly focus on providing safe, comfortable, and efficient services. In terms of safety, we mainly focus on improving the real-time updating capability of the maps so as to avoid safety issues introduced by the change of scenarios. In terms of comfort, we have built a full road network-level driving knowledge graph, mainly with the help of human drivers' driving experience to significantly improve the ride comfort. In terms of efficiency, we mainly use vehicle-road collaboration and traffic brain to improve travel efficiency. About cost reduction, that is how can we achieve a continuous reduction in the production cost of high-precision maps through AI-enabled scale production. Automated sensor data fusion is an important building block and the core capability for mass production of high-precision maps. The goal of automated data fusion is to fully automate the fusion of sensor data from multiple acquisitions, for example, the laser point clouds or road images, in a unified coordinate system. The main challenge lies in the absolute or relative accuracy of this fusion to the centimeter level. So how can we do that? Well, firstly, we divide this data by blocks or roads, and in each sub-block we perform the fusion of data and then connect and adjust the geometry of HD map elements across adjacent blocks to enhance the continuity of high-precision elements between blocks. The main problem of this approach is that it is difficult to guarantee that the obtained data are all perfectly aligned. To solve the problem, our solution is to improve the continuity of HD elements between blocks according to the data spatial distribution to ensure that the accuracy of this whole graph is consistent. Then we have innovated in three aspects. First is the multi-level graph optimization. We ensure the consistency of data fusion within the block by establishing a local graph within the block. And then the global graph between the blocks is established. And the second point is scenario-based association matching. We use scene recognition to divide road sections into many different scenes, and then design association strategies and matching algorithms. And the third one is a learning-based matching algorithm. We use a network that performs both overlap region estimations as well as feature point extraction to match and extract feature point only in the overlapping regions, which greatly improves the robustness of matching. Here, I'd like to give you an example of a result of fusion on a point cloud-based map. From the comparison, we can see that the fusion result of the traditional method has a serious misalignment, while the fusion result of our new method is completely correct. And the automated annotation of maps refers to the process of automatically generating HD maps based on point cloud and image data. This is the core driver of significant cost reduction efficiency. And in order to achieve high automation rate, we have to make a technological innovation this key step. In terms of the element recognition, we use a multi-level point cloud recognition method, and the result is much better than the result of one recognition. And on vectorized element extraction, we post-fuse the elements of this element to ensure high accuracy and high recall of the element. Thirdly, in the automatic modeling, we have matched the vectorized elements based on the lane level topography template, which greatly improves the topography generation and accuracy. Through the application of a series of AI technologies, we have achieved significant improvements in robotaxi, high-precision map production costs, and delivery time. The graph on the left shows the production cost per kilometer of robotaxi HD maps, and we can see a significant decrease in 2021 and 2022. And the delivery cycle of this new city light map, which we can see in the chart on the right, also has a very significant decrease in 2021-2022. And now I'd like to share with you our product which has focused on the user experience. First, safety aspect. And this section focuses on how we can guarantee the safety of autonomous driving by generating online maps in real time. We all know that the ultimate goal of L4 level autonomous driving is to remove the safety officer from the car, which actually puts very high demand on the map. And then through a lot of practice analysis, we found that real-time sensing alone cannot meet the high safety requirements. Here's an example which can show a few scenarios. The first example shows trees blocking the signage and preventing the accurate speed limit and other information from being sensed in real time at the vehicle. And the second example shows that the ground has been defaced due to construction and the real-time perception cannot identify the lane lines. The third example shows a situation where the old and new road markings are overlapping, so real-time perception is more challenging. And the fourth example shows that lane types are not clear, and the lane is actually a bicycle lane, but is not identified. So, can offline maps alone meet the high safety requirements? The answer is negative. This is because the road and environment changes so quickly that it is difficult to meet the demand for real-time updates by relying solely on the traditional offline map models. And the following also shows two scenarios. The first scenario is very common. It's the problem of road redrawing. The offline maps often cannot be updated in time, and the stored data can only reflect this scenario scene before the redrawing. And the second example, we can see that there is a temporary road, a block. We can only use the left side of this temporary road to cross. And then, in order to achieve high safety autonomous driving, we adopt the solution of fusing vehicle side sensing data with multi-source maps to generate this online map in real time. First, we use this camera add on the vehicle, and then generate BEV's feature map based on transformer, and then generate a real-time map on the vehicle side. Then we effectively fuse the real-time map on the vehicle side with the high precision map and the crowded source map, generate the online map. Finally, we make this map available to downstream sensing decision-making in the planning models we use. And the second aspect of the user experience is the comfort level. This section focuses on how to enhance the comfort level through driving knowledge enhancement. As we all know that knowledge is the ladder for human progress. In the field of AI, knowledge graph is also the ladder of progress for artificial intelligence. In the field of autonomous driving, through our practice and thinking, we also believe that driving knowledge mapping is a stepping stone to progress. While real traffic scenarios, as we all know, it is very complex, and this actually brings a great challenge. And now, here are two real-life scenarios. And now I'd like to introduce about this video clip. You know that it's actually introduced. It's the car trying to leave for the off ramp. We can see the ramp after the speed limit sign. If the automatic driving immediately perform the operation deceleration, means that the vehicle, there will be a sharp brake. Now let's watch this video together. Well, we can see that from this video, if the rear car doesn't follow the emergency braking time, in fact, there's a great potential for a car accident. And we will find that in some scenarios, if we turn left after the right turn, we will not plan in advance. Another video, please. From this video, we can see that at the very beginning, the car tries to make a left turn, and the right lane, in fact, there's no other vehicle. The best strategy is to turn right directly to the right lane. Then, in addition, in fact, we can see from the video that the right side, the car just for a brake. And from these examples, we can see that without the introduction of driving knowledge mapping, it will be difficult to ensure a comfortable experience. Then the construction of the driving knowledge map needs massive real traffic data as a support. Based on the Baidu Maps unique data resources of over 12 million kilometers of road network coverage and an average of 12 billion kilometers of track miles per day, we learn from hundreds of millions of drivers. Then through Baidu's leading artificial technology, we have built a full road network level driving knowledge map. This knowledge map, as we can see, contains multidimensional and rich driving knowledge, such as experience, the speed, timing of lane changes, etc. With the enhancement of driving knowledge map, the speed changes of autonomous driving can be more reasonable. The lane changes can be more adjusted and more timely. And as we all know, that autonomous driving, the ultimate target for them is to improve the efficiency, and this is also the third aspect of our user experience focus. Different from closed scenes such as high-speed and parks, in fact, urban traffic, as we all know, is mainly composed of three major elements: people, cars, and roads with strong dynamics, high openness, and a high degree of complexity, which actually bring a serious challenge for autonomous driving. If we only rely on local single-vehicle autonomous driving strategy, it's difficult to ensure efficiency. So our solution is to build a Baidu traffic brain based on Baidu intelligent transportation and the leading capabilities of Baidu maps to empower autonomous driving for efficient mobility. Then, by providing global traffic information such as real-time road conditions, events on the road, and ETA for autonomous driving, we can help autonomous vehicles choose better routes, which can significantly improve the efficiency. And then, on the other hand, the vehicle intelligence alone cannot perfectly cope with all the complex situations, and the vehicle road collaboration technology can effectively solve that problem. And that this is one of the important aspects of intelligent transportation. And we based on the Baidu ACE intelligent transportation overall solutions through intelligent information control, planning, and we have significantly improved the efficiency of traveling. Based on our many years of experience in the field of autonomous driving and our investment in maps, we have our long time practice and in-depth thinking about maps. And now I'd like to introduce to you our Apollo autonomous driving maps. In order to provide safer, more comfortable, and more efficient experience, now I'd like to introduce to you about this map. We know that it has 4 layers. The first layer is the static layer, which is the content of the traditional high-precision maps, including lane, level data, then topology data, and positioning data. And the second layer is the dynamic layer, including real-time traffic events, real-time traffic situation, real-time environmental changes, which relies on massive spatial and temporal data, and vehicle-road cooperation. The third layer is the knowledge layer, the core of which is our first-hand driving knowledge, as well as the safe driving. And the fourth layer is our driving layer, the fusion of knowledge and driving strategy to achieve a deep fusion of maps and perception, decision-making, and control applications, and the fusion of real-time data perception, data closure, and real-time updates to achieve high degree of freshness of the map data. If we define Apollo autonomous driving maps in one sentence, it would be knowledge-enhanced, multi-layered, and multi-dimensional new generation maps for autonomous driving. Let's take a different perspective. Let's put ourselves in the shoes of an ordinary user and see what this new generation of maps can bring. And there are 3 main aspects. First, more safer experience. For example, now as we can see that when there is a car accident ahead and the right-hand lane is occupied and the self-driving surface can plan ahead and slow down. And the second, it is difficult to distinguish between the old and new lines when there are changes in the field, so it is difficult to identify between these lines by simply using vehicle-side sensing. The third situation is more common when there is bad weather and then the road is there's too much water on the road. Then we need to use this real-time map. Now, a video of Apollo Go. Through this video, we can see that based on the Apollo self-driving map, our robotaxi can plan ahead to the left lane to avoid vehicles that are under construction on the right. Secondly, it's more comfortable self-driving. Here we have 3 scenarios. The first scenario is to turn left and then turn right. And through our self-driving map, you can turn directly to the rightmost lane when turning left to achieve a very better experience. And then the second scenario is that 500 meters ahead of us from 5 lanes into 3 lanes. And then through this self-driving map, we can plan ahead and avoid the braking and the waiting. And the third scenario is that if you leave for the expressway for the off-ramp, you can slow down from 120 to 30 gradually. Now another video, please. And from this video, we can see that based on this map, when the car has to turn left, we can plan ahead so that can provide a better experience for our users. And the last one is about more efficient self-driving. And here we have 3 scenarios. The first one is about green wave channel. The second is that when there is an intersection, it's about to be congested. If there's a car accident that takes up 2 lanes, we reroute ahead of time. And the third example is that we found through the self-driving map that the road traffic is very heavy, and from 7 o'clock to 7:30 in the morning, we avoid it in advance. Now another video. With this video, we can see that with the help of our intelligent transportation, we can get a more efficient travel service. Apollo self-driving maps have been applied in scale. First, Apollo Go is grown rapidly with the cumulative order rides reaching 1.4 million, maintaining its position as the world's largest self-driving mobility service provider. And the second, we have provided ANP pilot assisted driving solution that understands the user's requirements. And finally, Baidu Maps has taken the lead in launching autonomous driving level navigation product features such as urban lane level navigation, parking space level navigation, and intelligent traffic lights. For example, the lane level navigation in the middle, we are able to let users experience the exact same safe travel experience with autonomous driving. This is all that I have to present today. Thank you.
Thank you. Now we'd like to turn to Wang Jingdong to introduce about the application of the Wenxin big model in autonomous driving perception. Now let's welcome. Hello everyone, I'm Wang Jingdong. Zhizhou has shared with you about the map-related content. For me personally, I'm going to introduce about the autonomous driving perception, and my topic is an application of the Wenxin big models in autonomous driving perception. In our opinion, the sensor fusion is necessary to achieve L4 autonomous driving, and here I would like to take a brief look at how these 3 sensors achieve a complementary relationship. And we know that LiDAR point cloud and radar point cloud cannot provide very rich color information and texture information, and then makes them point and cloud recognition effect quite general. However, the camera can provide rich color and texture information to help improve the effect of the semantic recognition. And the LiDAR point cloud and cameras are limited in the weather condition, such as the rain and snow perception effect. And then at this time, the LiDAR point cloud could still provide quite a good result, and then radar point cloud still is relatively noisy and its resolution is relatively low. So at this time, we could combine the LiDAR and a camera to provide the information with high resolution. In addition, and we know that the camera is readily friendly to long-range perception effect. In fact, here we have experienced 2 generations autonomous driving perception, and then in the perception 1.2. And we have gone through 3 stages. The first stage, we mainly rely on the LiDAR point cloud and to assist the visual recognition of the traffic lights. So we have better applied the LiDAR technology to pinpoint the radar objects in stage 1, and we have added the multi-view 3D perception, and then together with the LiDAR point cloud, we have established the two-level perception fusion to increase the recognition effect. And at stage 3, we self-developed the radar point cloud perception algorithm, and to have the 3-level perception fusion, so we could have a delayed fusion based on the multimodality perception. And here in the late fusion, we basically use the rule-based approach, so combine the 3 senses perception, and we could have the rule-based approach, not learnable approach. And its generalization ability is not that good, so we have the generation 2.0 based on the early fusion, and here we have the multimodality end-to-end early fusion, and also we fuse the point cloud and then the surface representation of the images. In addition, it includes the visual perception at a long range and usually relatively good above 200 meters. In addition, we use the fish eye perception, and to achieve the free space prediction, we combine the 3 organically so as we could achieve the near distance, medium distance, and long distance to form the high quality of this perception. As we know that we need the lots of data and high quality data, so we apply the data mining and the automatic data labeling in the 2.0 generation. And here I'm going to share with you some challenges in the autonomous driving perception. Here, let's take a look at long-distance visual perception. And we know in such a scenario, the objects look smaller and resolution is lower, so big challenge for the recognition and perception. And in the long-range scenario, we usually encounter the larger scope, quite challenging for the perception. So we basically use the data at the road surface, and the road is flat, so we could take better use of the ground plane so as to achieve the long-range perception of the objects. The second challenge is that we know that the LiDAR sensors continue to upgrade, and also we have big challenges and big changes in the point cloud space distribution. So at the early stage, our LiDAR sensors was based on the Baidu LiDAR. Later, we updated it into the high-sense 3D sensor or LiDAR, and currently we are considered to use the solid sensors, and also the sensor upgrading has upgraded the distribution of the point cloud space. And you could see that it changed from the original sparse to the current dense features. And then we know that the 3D labeling is quite hard, so it is quite challenging for us to further apply the old sensor labeling into the new sensors. Now let's take a look at the long-tail data mining. Here we have 3 iconic examples, and the first is the RAN models, and we know that the frequency of special shaped vehicles do not just occur quite often, because you could see the shape is not quite regular, and sometimes they have some pointy parts, so it is quite challenging for us to perceive and understand them. So we could not localize special shaped vehicles and predict the distance quite well. The second is the forms and postures of pedestrians, quite big challenge, and also it's going to be a great challenge for the motion prediction and tracking. The third one is low objects and traffic and social elements. That low objects have been quite challenging, probably in perception, and then also we know the construction will also bring some problems for the perception. For example, the guardrail, and then it means that it is not accessible, so we have to localize those elements in the construction. About these 3 challenges, we have used the foundation model technologies to increase the perception of the autonomous driving. Here, I'm going to share with you 2 parts. First, we use the Wenxin big model autonomous driving perception technology to increase the perception capability of the onboard small model, and also we use the Wenxin weekly supervised pre-training for image to tap the long-tail data so as to train this model. First, let's take a look at this model, how it works. And first, we're going to label lots of the data. Here we know that it is easy quite get the 2D labeled data in the order of 10 million, but it is quite difficult to get the 3D labeled data. So here, how to use this data without 3D labeling is a quite big challenge. That is why we use the semi-supervised pre-training for images, so as to make full use of the 2D labeled and unlabeled 3D data. And then we use the method of an iterative self-training. We first train a large perceptual model on top of the 2D and 3D training data. Then we label the data without the 3D labeling with the 3D pseudo label. Then we continue to train a perceptual model. This is the foundation model, and through such an iteration, and we gradually improve the effect of the perceptual model, and also make the effect of the 3D tail labeling better and better. And so you could see in the following 3 examples, we are going to make it better in practice. And such a perception foundation model, it is not only used for vision but also for the point cloud, and then also used for the multimodality end-to-end solution. Here I'm going to mention that in the far vision perception scheme, and we actually also use the method with encoder and decoder pre-training, and also we have to take better use of the publicly available data sets, Object 365 and CO, and then such pre-training methods. And here we have to know that based on the method with encoder and decoder pre-training, and then our group DETR version 2 actually have a breakthrough of the 64.5 MAP in the standard open data sets. First, let's take a look at the long-range aspect. And in fact, we should scheme based on the distillation of the knowledge. And the pseudo-labeling skill is based on the knowledge distillation and pseudo-labeling. And as we know, in the network architecture, we usually include the encoder and also the head of the 2D testing and head of the 3D testing. And then we also use the distillation at 3 areas. And the first thing is at where the encoder come out, and we use the big model features to train the features of the 3 model. In addition, on top of the head of the 2D and then head of the 3D, we will do the distillation of the features and to this model. And then here we could see we have a tip in the training, that is to further use the detection head of the larger model, including the parameter in 2D and 3D, and directly as the initialization of this small model to further improve the efficiency and effectiveness of training. And here, let's take a look at the effect. And then this is the effect brought by long-range 3D perception. Here you could see this is scenario, blocked scenario, and in this photo we could see that the green box to the left is the ground truth, and the red is what we haven't predicted. We could see the comparison of the old model and the new model, and also we could see the great enhancement of the effect in the new model, either from the perception and the predicted vehicle distance. Let's take a look at the bumpy road. Still, you could take a comparison, the old to the left and the new to the right. And then we could see that not only the distance of the object's vehicle becomes more accurate, but also the direction of the vehicle is better predicted, and its angle is better predicted. And this is an enhancement of the capability. And then in practice, we could find more better results. Here are only 2 examples. Now let's take a look at the application of the large models in the multimodality early fusion. And here in this case, we could see that the multimodality early fusion scheme corresponds to the larger model that is actually trained by the semi-supervised solution. And how do we help the training of these models in this aspect? In addition to the distillation scheme, and we also use the pseudo-labeling in addition to the distillation at the encoder level, and also we use this way to help the training. Here are several points in particular. First, we use the deeper supervision. What does it mean? And we use the 3D prediction on the image and the point cloud. And for example, on the image side, we do the prediction of the 2D and 3D. This is the silos, and you're going to improve the training. Also, we have used the pre-training scheme because in our multi-modality scheme, we have both image encoder and the point cloud encoder. So the image cloud encoders are not actually trained under the multi-modality encoders at the very beginning. And it is the case for the point cloud. And here I would like to share with you that we downgrade such a scheme to end-to-end perception of the multi-view images. By doing so, we have achieved good results on the publicly available new scenes data set and currently we have achieved the best result in the case of the multi-view in new census 3D detection, and we can apply such a scheme to tracking in the new census, and we also have achieved quite good results. Now it has ranked the first in the tracking list. Now let's take a look at the effect of our point cloud perception. As we mentioned earlier, in the multi-modality early fusion scheme, we use the point cloud perception of the encoder pre-training. Then we first look at if only in this point cloud using the larger model of the scheme brought an effect, then we could see from the old model and new model comparison the results. And then in the force detection in the road test, we could see we have achieved load, but still we have some force detection for the graining barrier. And later we are going to combine further the big model and the small model, so to solve more problems. And also let's take a look at the overall effect of the multi-modality early fusion perception. Here it is an example that had been solved with great efforts. You could see at the left is a sprinkler watering court, and in front of the court it has the mist caused by the spray. In the old solution, we did not use the multi-modality early fusion solution, so we're going to identify the mist as a vehicle, and use the new solution. We could see we have solved this problem. Now let's take a look at the use of the large models in data mining, and this is the flow chart for data closed loop of autonomous driving perception. And here I'm going to share with you our technology for the data mining, and later I'm going to share more detailed technology about the data-driven system. In the data mining, we use the larger model scheme, and relatively to the previous perception scheme, but not exactly the same. And then here we use the weekly supervised pre-training for image, so as to help do the mining of the long tail data. Here I'm going to explain how we do the pre-training model, and then we usually have a large number of image pairs, and then we send our image to an encoder we call the image, and then the text corresponding to the image pairs is also sent to the text encoder. So we train the text by optimizing so-called contrast loss. And such an encoder trained has quite a good effect. It could handle the semantic recognition of what we call the open data set. This is quite different from our traditional ImageNet. For example, at the ImageNet 1K, we couldn't handle 1,000 categories. But for our model, we're going to train more than 1,000 categories, even thousands of categories. We could take advantage of such a property to do more data mining. After such a model trained, we could, in our autonomous driving database, we could do the database construction. But why first? For example, in the streetscape data, we going to first locate the possible objects, and then we use our recent detection solution called the group data V2 so as to locate the possible objects better. And then after localizing the possible objects, we could get out the image blocks where the objects are located and put them in the image encoder to form a vector, which is the construction of the base library. And then we do the mining. We have two ways. One is that if we do not have the image we need to mine, we can directly mine through the text. And for example, here is we inputted plastic back into the text encoder to form a text feature. This is the text representation of the vector. And then we use the fast vector search algorithm. In the online library, we could quickly find these images that may be the plastic bags. When we have slowly found some images of plastic bags, we could also input the image into the image encoder to extract the visual representation and then form the similar vector search. In fact, in such a process, our initial image search results might not be so accurate, but after the number of our search is on the rise, we could get more and more images returned, and then we could train the fine classifier for further filtering so as to improve our data mining effect. The following are some examples of our data mining and how it ultimately helped us to improve the perception of the autonomous driving. On the left are some typical examples. For example, children on the road, delivery vehicles, wheelchairs, plastic bags on the road, fire trucks, ambulances, so on. Those are the examples of our data mining. In terms of capacity enhancement, we divide it into two categories. One is that we already have the capacity and we have improved it through the data mining. For example, detection of children, the false detection of the plastic bags, because we know it is quite important to detect the plastic bags. If we could able to well distinguish between the plastic bags and other things, and then we are going to have a big improvement and will not put great challenge to the PNC, for example, the emergency braking. And the second is that we do not have a capability, and now we have got the new capability through the mining. And before, we could not distinguish the fire trucks and ambulance, but we found that those two vehicles have the higher right of the way. So if we couldn't well identify them and tell the difference, then we're going to help the downstream driving strategy advancement well. And in addition, one thing quite interesting that we're going to have some small animals on the road. This is quite interesting. Probably some small animals or like horses on the road of Chengdu. Also, we could see the sheep on the secondary road in Chengdu, and so through the data mining, and we could further enhance the autonomous driving perception of the vehicles. And last but not least, I would like to end my presentation with one sentence. The big model has already become the core driver of the autonomous driving. Thank you very much.
Thank you, Mr. Wang. Now, Mr. Li Yang share with us the closed data loop of automatic driving in Apollo. Good morning, I'm Li Yang. Now I'd like to share with you some insights and observations on the closed data loop of automatic driving in Apollo. First of all, autonomous driving is a matter of continuous learning, and we know that the unmanned vehicles drive in the cities and it will encounter different problems and unexpected new scenarios. And as we can see that it is even possible for us to see a flock of sheep crossing the road. And for these long-tail scenarios, it's a challenge for us to resolve. And for these vehicles, if they can run on roads, then they can search for this mass data. And the problem is, how can we leverage on this data and to improve the safety and comfortableness for this experience? And this closed data loop, we believe that is an important fundamental structure for us to achieve the continuous learning. But it also has posed some brand new challenges. On the one hand, it has brought about pressure for data storage and data annotation, and the full data postback model is not sustainable anymore. And on the other hand, and our target is to leverage on the data to improve the driving capability. But the computing volume of iteration will be improved. So how can we find out a high value or high purity data from a copious volume of data? And the second challenge is, how can we use well of this data to improve the intelligence level of the algorithm? To answer these questions, we designed the closed data loop in Apollo. First of all, the whole system is composed of the onboard and offboard sector, and the whole data closed loop is composed of data purification and data digestion. And then data purification will be applied both on board and off board. Its target is to find high value and high purity data, and the data digestion is deployed in on board. It is to improve the intelligence level of autonomous driving. And now I'd like to present to you our design in high purity and high digestion data. First, we need to establish a channel for data purification. We know that the scale of data is not the only important element that we need to consider, because the purity of data is another factor that we need to give it to consideration. Here's an example to show you how can we improve the purity of data. As you can see from this picture, there is a puppy, and it has been detected by algorithm, and such kind of data is called guide sample. And on the right, as we can see, we have used these white dots to label them. So we want to find out similar pictures of such dogs, but this will also cause the pictures mixed by the system. And from searching these pictures, for example, if you use the nearest neighbor search, we can use these blue circles to label them. And such kind of method is called guided mining. As you can see that this method doesn't use its own information in testing. So we can use an overall, a holistic approach to see this guided mining. We can use dotted lines to show the decision boundary. Any data in this boundary are uncertain, and this data will bring about extra information. So we also call this uncertain mining. And while we are obtaining this figure, this data, we know that there's no label, but we can use annotation to get this label. After we obtain these labels, we can use the model training to change the decision-making boundary of the models. So, to put it simply, data mining and annotation are both important methods to improve the data purification. And then, according to that, we have designed the data purification channel of autonomous driving. From this picture, we can see that the data flowed into the system, and the core composition is an inference engine. And the inference result includes data of the data features and the labels predicted by the model. Another important element is the model repository, and it has large, big models which can use inference engine to obtain features and labels of data, and they can also be used for sample mining with the vectorized search, and for those smaller models, it can also be used for data purification. And but these smaller models are usually actually used on the cars, and these data actually have to be used to improve the efficiency. Despite that, and we can use a classical integrated learning method to understand the uncertainty of the model against the data. And from this inference engine, we can inference about the attributes of all the data, and based on that, we can further provide complex mining rules so that we can achieve more complicated and targeted method. And from this architecture, we can find out that the efficiency of this purification decided by the efficiency of the inference engine. And this efficiency is decided by the data fetching speed, and it can be optimized by the documentary system innovation. And now we have cooperated with the Baidu team, and we used the Baidu flow data structure and integrate them into our platform, and we have increased the efficiency of data fetching by 10-fold. And if we only rely on such kind of cloud data purification, it's impossible for us to meet the demands for large-scale autonomous driving, because the upper limit of storage space cannot support the digital return. So we also need to deploy the channels of data purification on board. And this is quite different from the off-board system. For example, it has different way of integrated learning. And the integration, some methods, operating methods off-board cannot be used on-board. And to put it simply, the purification of data is actually a different model, and it's a dual dimension deduction. And while we are obtaining such pure data, another challenge is how can we digest these data in an efficient way and translate it into a intelligent driving capability of vehicles. Now, the world we are in is changing, and the data the vehicles have searched for are also collected, also changing. And how can this system perceive the change is an important matter that we have to consider. And the whole system is not a single model. It's actually composed by a lot of differentiable and non-differentiable modes. And how can we optimize these models is a big challenge for us. And another issue we have to consider is efficiency of data digestion, so that we can reduce our demand for human labor and in the end, lower the cost. And now I'd like to introduce to you about our practice in three aspects. First is the automation and joint optimization and the data distribution. First, some concepts based on continuous learning and AutoML. Actually, we have designed a automated training engine, and the data flow into the training engine through data cache and sampling. And this is just like the experience playback mechanism in continuous learning. And we need to use a model set, which include not only the best model, but also the medium models produced during the whole process. And we will use a synchronous inference engine to test, so that the ultimate output is a candidate data and model set, and it's called the Pareto front. And we think that is composed of parameter and superparameters. And the parameters define the static status, and the superparameters define the dynamics of the whole model. And we combine both these two parameters, and we use gradient optimization as well as non-gradient optimization, and we have borrowed the evolutionary algorithm-based structure. And it's quite different from the traditional way. And we have perturbation of the whole model, and this is actually a concept put forward by Rich Sutton and Jordan Ash. And in practice, we figured out that this parameter perturbation can be used to improve the robustness and stability of the whole model. And the parameters could be used for initialization and the pedal cloud distribution training. And the step length of training. We don't need to wait for the model convergence. We can set up some shorter step length so that we can achieve the automatic hosting capability. That is to say, we can have this all unmanned training mode. Let's just take that example of that little puppy again. We can use feature searching and mine a batch of puppy data, and then we can send this new data and old data together for automatic training. As we can see that each dot here is actually a model, and during the whole process of training, the efficiency has been improved. And ultimately, we figure out that we can achieve the improvement of both the small target and the overall target indicators. So this training engine can not only be applied to solve such problems, can also be used to improve the efficiency and result of this model. For example, can be used to solve the low greenery problems, the fence issues, and the suspended plastic bags. And when we are trying to optimize such kind of system, we can figure out that these data are sent to the training system by a data set. And in this process of iteration, the whole model's efficiency has been improved continuously, and we even didn't detect any saturation of data. And the example aforementioned is about the optimization of a single model. But autonomous driving is a complex system with a lot of models, so we need to focus more on the joint optimization. And the way of optimization in this autonomous driving is to have our own target and integrate this target. And the whole system has a lot of non-differentiable mode, so it's difficult for us to calculate about their gradiency. And we also need to take into consideration about this impact on the downstream. So the method we use is like a coordinate descent. A good example of a joint optimization is behavior prediction, because from this picture you can see that it's in the middle part. It has upstream and downstream sector, and this behavior prediction model consider both the trajectory and the intention of the obstacles. And this prediction model and its data and that its complexity is relatively high. First, we have tried and a new way to collect some data and use an engine to optimize the assessment and indicator. And this indicator is composed of different types of objects, for example, bicycles, pedestrians, etc. And from the result here, as you can see, that we figure out these indicators have been improved dramatically. But after we put this model into this end-to-end system, we find that this efficiency of the simulation has been decreased. Why? We believe that that's caused by the inconsistency of the prediction indicators and the simulation indicators. Let's use this typography graph to give you a better understanding. Let's just assume that if the dots are in red, are in higher region, then the indicators are better. if we just look at the training indicators using gradient optimization, yes, we can indeed find a area which is red and a higher indicators. But if you match that for the assessment target, then we will find that it's not in a high status. So based on that, we establish an engineering architecture, and we have done the simulation review. As you can see here, even though there is a slight decrease in the prediction indicator, but the efficiency of the simulation has been improved considerably. And this example is just about the impact of the data distribution to training. And we believe that the data construction capability is closely related with the data distribution. And data distribution actually is a very critical concept in machine learning. Why? Because the deep learning is the main method for us to drive data, and the core principle of deep learning is to minimize the risks and experience. As we can see, there is here the W and the V. They are the weights or density of each sample during the training and during the assessment period, respectively. So, as you can see from this, if W is different from V, and then the model we gained from the training is not the best during the assessment period. So, the core problem, the core challenge for us is how can we find a correct data distribution. So we designed a management and exploration method for data distribution. It is divided into two parts. First, we has pre-tested the data distribution and manage it in a unified way. And this pre-test can be set by human, can also be gained from learning. And after this pre-test, enter into the training engine, and the engine can use this data distribution as a super parameter and use it for exploration or searching. After we figure out better distribution model, then we can use a feedback system to correct the pre-test. And another problem is how can we describe this data distribution. We usually use labeling and a scenario-based method. And we usually ask 3 questions to match different scenarios. They are namely about the behaviors of the vehicles, behaviors of obstacles, and the types of obstacles. Then we can collect these data of different scenarios. Here I'd like to introduce to you our experiment we do to learn about the data distribution. So it's actually based on the idea that the platform of the closed data loop is actually managing all the model training. And so our log has a lot of models and indicators. So, for example, in the just mentioned training, we figure out that in this log there are actually a lot of models, indicators, and matching data in simulation. So naturally, we think about whether we can train a linear predictor, and its input is the prediction indicators of different scenarios, and the output is the indicators of simulation. And another example is that, for example, there's traffic data, some data from traffic circles, and we had the data of emergency brakes, and the main scenario here is the vehicle circling about this island, and the obstacles entered into the island. And if the vehicle cannot predict well, and that it may has an emergency brake, as such distribution is not the real distribution, but it can contribute to the assessment capability of the platform. And we can also use this data distribution to provide guidance to adjust our pretest or the data distribution in indicator assessment, so that we can improve the consistency of the training indicators and assessment indicators. And in the above-mentioned example, we can see that we have lowered the cost by lowering our demand for simulation testing. To sum up, we have put forward the design for a high purification and high digestion. And this purification has integrated small models and big models to achieve data mining and automatic labeling, and high digestion has been integrated through models and data. And at last, we hope that the high purification, high digestion of Apollo can provide more insights and inspiration for our colleagues in the whole industry. Thank you.
Thank you. Thank you for sharing. Now I would like to welcome Wenxin to share us on the topic of independently developed AI chip innovation empowers high-level autonomous driving from AI to end-to-end computing power. Now let's welcome. Good morning, everyone. I'm Wenxin, CEO of Wenxin Tech Company. Quite honored to share with you. As you know, in the past several years, intelligent vehicles have been developing quite quickly, from the traditional L2 of the assisted driving to today's robotaxi and then high level of autonomous driving. And then the self-developed chips are also developing quite quickly, so I was quite curious and how the self-developed AI chips are performing in the higher level autonomous driving. Today I'm going to share with you about this scenario. And before I go to the tag, I would like to introduce the Wenxin technologies. And for our company, we could use one sentence to summarize: persistence is the key to success. And we used it to be one department of Baidu. And at the first day of 2011, and we entered the AI industry. Then we focus on the AI computing related work. And then at the beginning, we used the FPGA, the field programmable gate array, to speed the computing speed of the AI. And from 2011 to 2015, and we have deployed more than 5,000 FPGA in Baidu data center. By 2017, we have deployed more than 12,000 PFGAs in total. At the same time, we have published 3 papers at hot chips and also presented our papers at some top conferences. We have published the XPU architecture for the first time at the hot chips, and then in 2018 we thought that there are going to be changes in the architecture of AI computing, so we decided to develop our own AI chips and officially designed the Wenxin series. And by 2020, the first generation of Wenxin chips began to have the larger scale deployment. In 2011, we became independent. By 2022, we had the second generation chips, and then have been applied in industrial field and autonomous driving. And this is the milestones of our development in the past 10 years. And the domestic AI chips with a large computing power started relatively late. In such case, we must speed up the iteration, and then the speed and intensity of our iteration cannot be lower than the advanced foreign products. And the Wenxin has already mass-produced 2 generations on such a high-intensity iteration. And this is currently we have the third generation in development, and also we also are working on the fourth generation, as you could see from the photo. And this is our first AI chip, 14 nanometer process, and here I have taken it. You can take a look. And this is it has used the advanced HBM or high bandwidth memory, and we also use the 2.5D package. And then this chip has been deployed in Baidu data center for more than 20,000 pieces just after mass production. And after 1 year, we had mass produced the second generation, 7 nanometer. This is quite advanced. This is the second generation, also quite advanced. Use the SPU second generation architecture. Also, this is the first AI chip in the industry to adopt the GDDR6 graphics double data rate version 6 memory technology. And also we are developing more advanced third generation. The iteration is quite quick, and also based on our AI chips, we have released a series of AI acceleration boards and AI servers, including the high-performing AI servers for training. Here I'm going to share with you the mass-produced second generation cloud-based generation general-purpose AI computing processes. And then you could see that currently we have models, even they could not be adapted to each other, we cannot meet the AI needs. So we have to have the general purpose AI chip, and then the second generation chip adopts the latest generation of the SPUR architecture, which has been iterated over the past 10 years and significantly improved its visibility and ease of use. And chip's algorithm power is quite strong. It has the 128 TOPS and 16 bits, and then 250 TOPS and 8 bits. And then we use the 7 nanometer advanced skills, and this is the industry's first artificial intelligence chip using the RDDR6 high-speed memory. And then we have quite advanced chips, and with a high algorithm power. Also, we support the visualization, support the interaction between chips, support video encoding, decoding, and a series of comprehensive functions. The chip memory has 62 gigabytes, quite big, and also the memory bandwidth is quite high, could reach about 512 gigabytes per second. And then let's take a look at the self-developed AI chips in the market properly. You're going to be curious, what are your advantages here? We have 3. And first, we believe that the Wenxin is one of the few chips that could be deployed and applied on a large scale in real system. And we have more than 10,000 chips deployed in different areas like industry, transportation, finance, medical, education, and also we could see different areas. And the second, our ecosystem has been the best in the world, and we have the perfect adaptations with all processes or operation system or service in China. And finally, this is it is quite flexible, easy to use, and we know iteration quite quick. We have different models. So Wenxin has provided the SDK or software development kit, so as the developers could use it as the foreign GPU. So this is quite good for the quick iteration. We have so many AI chips in China, and for Wenxin, I think it is one of the few products that could be implemented on a large scale in many scenarios. And then we could use it in the vehicle to road coordination, logistics and system, intelligent transportation, and then the transportation related fields. And then we have a comprehensive and large-scale implementation in smart medical, smart parks, finance, large-scale computing centers of the internet, education. We have many good cases, and it means that it is welcomed by the customers. Now I wanted to introduce about the product technology and the market development, and later I'm going to go back to about its work of the high-level autonomous driving. And then we know today it's a robotaxi or the high-level autonomous driving system, and it's quite complicated. And we know that all the advantages accumulated by Wenxin data center, including its high performance, visibility, and its use of its easy of use can well enable today's high-tech autonomous driving system. And currently, the Wenxin Generation 2 have been fully adapted to the Baidu robotaxi system and also being used in the actual road. Here, I'm going to share with you our work. The high-level autonomous driving system have a quite complex computing system. Generally, it uses perception model, localization models, and control planning algorithms end-to-end computing. And the number of models may be dozens, and latest model in the industry will be applied to autonomous driving system very quickly. So it requires very cost iteration of the algorithm. It requires quite high computing power because there are latest models. It has quite for us to have a quite high requirements for the latency. So we have done a good job of supporting the whole robotaxi, includes the AR part. Also done good performance comparison with the most mainstream graphic card in the industry using the Wenxin Generation 2. Our performance is better than this graphic card, and our power consumption is less than half of it. And we also did a comparison of the performance with mainstream AI accelerator cards. Our performance was more than twice as high as its performance. We also did an end-to-end test, and we achieved the leading performance with less than half of its power consuming. And then, as you could see, that this is our work, and we haven't done the test, either simulation or the actual situation. And currently, we basically haven't matched the customers' requirements. Now, I'm not going to elaborate more. This is some of our work in the overall system. As you could see, the whole system is running very quickly and smoothly, and in its performance and stability fully meet the customer's requirements. Here I'm going to make a summary. Today's high-level autonomous driving computing system is very similar to the data center system. Its algorithms are quite diverse, and the speed of algorithm iteration is quite quick, and the complexity of algorithm is getting higher and higher. And so our computer system have to meet these requirements, or it cannot support so many complex algorithms, and especially for demanding scenarios. And then we have to make sure it operates properly. It has to be quite good for the programming and transplantation. If not, we cannot quickly adapt to the most advanced algorithm and cannot make sure its performance. Finally, its stability should be very good because the vehicle system and actually have high requirements for the stability compared to the compliance system. So we have to make sure the software and hardware as a complete system quite stable. Last but not least, I'm going to share some my takeaways. Currently, I have been working in the autonomous driving for many years, and we know for the onboard computing system, we thought it was a closed system, and so we have to have the quite in-depth software and hardware bespoke customization, but still, it was quite popular 5 to 6 years ago, but now we don't think it is the real case because we have to make the onboard computing system quite open so as to provide the users with high computing power, high generalization so as to meet customers' personalized needs of the computing system. And then for our Wenxin, and after decades of iteration, we're going to consider the SoC system on a chip and so as to make innovation. Thank you all for your listening. Thank you all again for sharing. Now we'd like to welcome the last speaker, Wang Liang, to share with us the symbiosis of an L4, L2 plus technologies in the era of intelligent vehicles.
Good morning, I'm Wang Liang. Just now, my colleagues share with you the full-stack technology in Baidu. Today, I'm going to share with you the technology symbiosis of L4 and L2 in the new era of intelligent vehicles. As we often say that the autonomous industry is experiencing a once-in-a-century change, and the electric vehicles and the intelligent vehicles are coming at an accelerated pace. The first stage is electric vehicles. With support from government policies and technological progress, we witnessed the launching of electric vehicles in 2019 and 2021. Electric vehicles could be found everywhere. And after that, we came into the stage of the intelligent vehicles. We believe that in 2023, and the vehicles with city road assisted driving capacity will be launched. And the third stage will be the stage of smart EV. We predict that the user's demand for intelligence will be close to autonomous driving, which is what we call L4 level autonomous driving. Let's look at the evolutionary trend of L4 technology. According to Baidu's internal planning, we believe that in 2025 we will cross the technological divide in autonomous driving in restricted areas, and our robotaxis business model will be initially verified, followed by a new phase of a commercial operation in multi-city areas, which means the number of scale of a robotaxi will increase significantly. And Baidu has been in L4 automatic driving for 10 years, and it has achieved a lot of results. For example, in safety, our operating test mileage exceeded over 40 million kilometers. And in terms of scale, our Polo Go has been applied in many cities, and our rides has exceeded 1.4 million, and we are already the largest service provider in this aspect. And in this year, and we have the fully driverless business operating in Wuhan and Chongqing, which is a milestone in China's automatic driving. And these 10 years of efforts has given us the confidence to use autonomous driving to empower intelligent vehicles. But confidence is not enough. We also need a strong competitiveness. And now, in this era of intelligent vehicles, how can Baidu start from scratch to launch a good product? A good product is can be launched with a good definition. For example, now in China, and most of these products are high-speed navigation, assisted driving, and memory parking. And the data shows that in China, over 70% of the city commuters use vehicles, and we believe that the L2 Plus product will be the main trend in the future markets, and Baidu will launch an L2 Plus navigation assisted driving flagship product, ANP3 version, in 2023. And we believe that these pragmatic products and should be customer-centered, so that we can provide the best value for our clients. And in terms of the hardware, we also believe in pragmatic concept. And the intelligent driving computing unit has used the smart driving domain controller of Baidu, and with 2 NVIDIA Orin-X chip and 500 TOPS. And in terms of sensors, we have used 8 megapixel HD cameras with a viewing distance over 400 meters, and we have used the state-of-the-art semi-solid laser radar. And if a client wants to choose a product and whether they can use it on a daily basis, the main reason is that it is safe. And so we believe that laser radar and the visual sensoring are equally important and irreplaceable. So we have made efforts for 4 years to establish such a Apollo Light. And for these 10 years, we are now leading in algorithm, understanding, practical experience, and data storation. And the LiDAR is a mature and reliable perception system. And the ANP3 vision and LiDAR these two systems can operate independently and with low coupling, and is probably the only domestic environmental perception solution that can achieve the true redundancy. And the front end of light perception system is based on the 2D object detection and the 3D pose assessment, and its observation has input from mono tracking and multi-camera fusion, and it has achieved a great result in most scenarios, but with the scaling up of testing, and it sometimes fail to solve the corner case problems, and then it has met its bottlenecks. So this year we have upgraded the visual sensory frameworks and launched the second generation of Light++. And this system has transferred the forward-looking features of the transformer to BEV, and has pre-fusioned before the tracking and output the perception result. And in the spatial fusion stage, the position encoding transformation is converted from the global BEV space to the local camera coordinate system to eliminate the discrepancy caused by the difference of internal and external camera parameters. In the time sequence, we fuse as much as possible the main vehicle motion with multi-frame information to improve the obstacle dictation stability. And Light++ has lower reliance on post-processing for multi-camera fusion, fewer computing power requirements, and better generalization capability. Compared with the previous light mono perception post-fusion strategy, BEV's time series perception has extremely high requirements on the quality and quantity of label training data, and the continuous production capacity of data determines the efficiency of the model evolution and iteration. And with 4 million kilometers of test miles accumulated by L4 robotaxi in different cities, they can ensure the diversity of data, and the full amount of real-time sensor data during the test has now been uploaded to the cloud, and by getting rid of the reliance on 2D annotation, L4 perception results fused with LiDAR information naturally become the annotated data for BEV models and can be directly used for model pre-training. And to further improve the quality of labeling using 4D data recorded by the regional sensors, which is space, time, and temporal data with image and point cloud large model technology, we build offline pipeline channels for more refined and complex perception calculation. And with the automation rate reaches more than 90%, the data production rate can reach millions of frames per work. And the second feature is familiar road or 熟路. And now we have established an online map learning route without HD map. And this is the common method taken in this industry, but it also has some problems. As long as the algorithm has problems in sensing the road structure of the physical world, the behavior of the vehicles will be difficult to predict and bring great safety problems. And we believe that if you want to improve the user experience, HD maps are indispensable, is a must-have. And the target of ANP3 is to improve the safety of driving. And our route has used the advantages accumulated in these years and lowered cost of mapping. Despite that, we have developed our online map learning capability to cope with the problem of upgrading of scenarios. In order to improve the generalization ability, expand the map coverage scale, we have used the vehicle side algorithm and significantly reduced the map production cost. And the first step is to reduce the burden in the map data collection. And originally, the area was reduced by means of the same route and multiple collections. Now, through the optimization of the online NPC algorithm and the upgrading of the map point cloud algorithm, we have collect data only just by one time, which can significantly reduce the external cost. And the second step is to reduce the layers of positioning. Originally, a map required the production and storage of 3 layers, and now we can rely just on one landmarking positioning layer to support that high precision self-positioning of urban roads. And the last step is to slim down of map element labeling requirements. And this high precision map contains both numerous road elements in the physical world and also needs to be labeled for the complex correlation correspondence needed for autonomous driving algorithm adaptation. Take the intersection traffic light recognition as an example. Previously, we need to label each light head individually, and the light also need to be used to match the lane line, which was extremely complicated. Now we have improved the ability to sense traffic lights, understand the semantics of these scenarios, and so we have established a binding relationship with the lines. And like sensor solutions, maps need redundancy, and this rely on a strong perception. An accurate real-time road structure perception is one of the most critical aspects. And we have designed and developed a BEV-based pure vision real-time online map learning framework. And in terms of model design, we based on the transformer combined with the characteristics of road structures. We have added road geometry and road elements, instance level query online vision. And as with the BEV obstacle perception solution, the key to the success of BEV real-time online map lies in the quality and the scale of this data. And it is quite difficult to collect this data and correlate the multi-view temporary road structure data. Data capacity and quality are the biggest obstacles. So to solve this problem, we use the Baidu HD maps and L4 multi-location coverage, which has effectively helped us to solve this problem of automated data production. And we have used the vectorization and temporalization steps, and have ensured the data quality and achieve pixel-level accurate annotation. And as you can see, we just talked about the autonomous production and the quality guarantee and continuous supply. And according to my experience, I believe that the data will play a more significant role. As you can see from this bar chart, it has reflected the different technological pressure we face during different period of R&D. And as you can see, we have invested a lot of resources and energy in data research and application. And in the future, we will transfer from the model-centric to data-centric of our developers. And I believe that intelligent vehicles should have the capability to evolve itself and grow itself. And I really also believe that the software and hardware are just like the body, and it can provide a self-mobility capability for intelligent vehicles. And the data is the fuel that can drive the experience and the capability evolution, which is the soul of the intelligent vehicles. And we hope that we can provide data added value services for ANP3 clients and and provide a better value for our end clients. And this is about a diagram of the architecture of the data closed-loop technology stack we built during the L4 R&D process. It includes the acquisition of raw data from the vehicle side, online, offline data mining, and purification, data labeling, and training. And this mature architecture supports us to practice our data-driven R&D philosophy and to continuously transform data into driving capability. Now we already have created an innovative data closed-loop SaaS product for internal and external users through the whole life cycle management of data mining, labeling, and we have realized the evolution of data-driven intelligent driving capability. And as for the data collection, we have been able to target online mining of the long-tail data most needed for each model task. And through dynamic mining and vehicle cloud interaction technology, we are able to do accurate dynamic and low-cost mining of data fragments needed to supplement model AI capabilities in a targeted manner. And the huge amount of data is also a big challenge to data digestion, model stability. And now we have already achieved the capability to enable daily, weekly iterations of the model and rapid fixing of high-performing problems. And let's review the AMP3 pilot-assisted driving features, safety, road familiarity, and good experience. Safety we have a guaranteed safety through our Baidu L4 technology, and for road familiarity of Shulu is actually the only domestic smart driving provider that is proficient in both autonomous driving and mapping technology, and it has created a leading and wide coverage and low-cost intelligent driving high-precision maps. And in terms of experience, the data mining system tailored to the smart driving model dynamically recovers high-value data, and it has given models equipped with AMP3 the ability to self-evolve. And now, I'd like to share with you a video of our R&D. Currently, AMP3 has been tested in Beijing, Shanghai, Guangzhou, Shenzhen, and many other cities, and will be launched in public in the summer of 2023. And now, A second problem I'd like to explore with you is the problem how Baidu will leverage L2 plus product to feed L4 technology and accelerate the commercial application of robotaxi. Let's just imagine that if we scale up the operating of L4, it means that there will be a lot of long-tail problems. And the biggest difference between L4 and other AI applications is the need for a safety guarantee and data-driven autonomous driving system. And how can we use data-driven way to check its safety first? We know that AI needs training data before solving a problem. Often, it's not a problem corresponding to only 1 or 2 training samples, but a software case behind the need for several times or even tens of times of the data. And we believe that the best path is to achieve driverless commercialization, is to achieve technology accumulation in a limited area in the early stage, and try to solve the long tail problem. And this is exactly what we in Baidu has done. We plan to exceed 1 million users in the next 3 to 5 years, and the million volume of L2 plus passenger cars will effectively collect and supplement the data for needed for solving the long tail problems. And then we see that in 2025, L2 plus products will cross the consumer divide, and L4 business models will be run through in local areas and cities. And this integration will achieve autonomous driving more quickly and efficiently than in any single path. And now we have started from scratch, from zero, and has launched this leading product of ANP3. And then in 2023, we plan to finish the technology layout. And then we have carried out the unification of L4 and L2 plus overall technical architecture, the unification of visual BEV scheme, and with the launching of Smart Drive ANP3 products in 2023, the subsequent synergetic flywheel of L4 and L2 plus technologies will work together. And now the final concluding part brings me back to the keyword in today's sharing, that is symbiosis. The definition is can be found in Baidu, and this integration of L4 and L2 technologies will benefit each other. Thank you. This is my sharing. Thank you for your sharing, so that we can have a better understanding of this automatic driving. And now Baidu is very confident about the future of autonomous driving, and Baidu insists on innovation first. In 2023, Apollo will continue to expand its service, and I want to thank you for your watching and listening. And any suggestion will be welcome. And we hope that every autonomous driver will grasp the opportunities today and meet the bright future together. This is the end of this meeting. Thank you.